Hello, today we're going to talk about normal distributions. Normal distributions are described by a special family of bell-shaped symmetric density curves. They look like this. See how they're bell-shaped? They're symmetric. Same thing is on the left and to the right of the mean. Normal distributions have the same overall shape, and the mean is always the center. So this right here is the mean, and that's the standard deviation. There are very important statistics. We'll be using these throughout the entire year. The standard deviation occurs at these points where it goes from being concave down to concave up. In calculus, if you've taken calculus, you know that those are called inflection points. If you haven't taken calculus, you don't need to know that those are inflection points. There's a rule, we call it the empirical rule. The empirical rule is a 65, 95, 99.7 rule, which says about 68% of the data is within one standard deviation of the mean. So one standard deviation up and one standard deviation down covers 68% of all the data. 95% of the data, the middle 95% of the data is two standard deviations up and two standard deviations below the mean. And 95% of the data is in that range. So 99.7, or pretty much 100% of the data, falls within 3 standard deviations of the mean. So if there are women between the ages of 18 and 24 years old have heights that are approximately normal with a mean of 64.5 inches and a standard deviation of 2.5 inches, draw the distribution below with 1, 2, and 3 standard deviations from the mean. So first we need to draw a nice normal curve. Hopefully you can draw it a little bit more symmetric than mine, but it's good for now. 64.5 is our mean, comes straight down here, and our standard deviation is 2.5. So at this point, it's 2.5 above that, which would be 67. And go that same distance out, and now that would be 69.5. Go that same distance out, and it would be 72. So that's 1, 2, and 3 standard deviations above the mean. Now when I go back, this right here is 62. Back that same distance, 59.5. Same distance back, and we get to 57. So that's 1, 2, and 3 standard deviations below the mean. You can see very little data exists down here. Which height is approximately 90 in the 97.5 percentile? All right, now these get a little tricky. The percentile is everything that's below. So if I look from 64.5 and below, that's going to make up 50% of the data. We know between 62 and 67, that's 68% of the data. So that's 34% and 34%. Now, how much is in this chunk? Well, we know that 95% of the data is here. And if I take 95 minus 68, I'm going to get 27. Divide that by 2, and 13.5% of the data is on each of these sides. That's supposed to be 13.5. All right. So if I add all of these up, I should get to 95%. So this is 50. If I go one standard deviation up, that's going to be 84%, the 84th percentile. Now if I add 13.5% to that, I should get 97.5. So the 97th percentile will be at 69.5. Now the next question, what percentage of the heights are 62 inches or lower than 62 inches. So 62 inches are here. We know this is 50%, and that's 34%. So 62 and lower is going to be 50 minus 34, which is 16%. What percentage of the heights are 62 or greater? Well, if 16% is lower, then subtract from 100 to get 84%. All right. Now we can get to the standard normal distribution. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Whenever it's written like this is the mean, and this is the standard deviation. And these represent the z-scores. So this is 1 standard deviation above the mean, 2, 3, and so on. Now we can use the standard normal table to find these answers. And in class I teach you how to do that. But mostly we'll use a calculator. So I'll show you how to use the calculator. So if we want to find the percent of values that are below 2.2 standard deviations above the mean. So we want to find the probability that is below 2.2 standard deviations above the mean. So that's, we want to find the probability that my z-score is less than 2.2. Well, if I drew a quick sketch of my graph, 2.2 is going to be like right here. So if I shade this in, if the area under this whole circle is 1, this is going to be really close to 1. I'd say 0.98, 0.99. To use our calculator for it, we're going to get out our calculator, we're going to hit second vars, normal CDF, which is number 2. We're going to go from negative infinity to 2.22. 0.9867 or 0.9868 because it was a bigger number than 5 after that. So about 98%, 99% of the data is below 2.2 standard deviations. Now if I want to find the percent of the data that's above 0.75 standard deviations, I want to find the probability my z is above 0.75. So if we drew this out, this is R0, R1, set 0.75 is about there, and it's going to be to the right. I would guess that that's about 30%. Let's check it out. We're going to do a normal CDF. Our smallest value is 0.75, and we go up to infinity. So make a big number there, close it off, and it's 0.2266. So about 22.66% of the data is to the right of 0.75 standard deviations. Now if we want to find the probability that my z is between 1.75 and 2.25, let's draw it out again. So 0, 1, 2, so 1.75 to 2.25. That's got to be a real small number in here of what I shaded in. So I would say that that might be 2%. To figure it out, I'm going to do a normal CDF from 1.75 to 2.25 to get 0.0278. All right, now if we want to find this probability something is between these two values, probability is between negative 1.24 and negative 0.58. So if that's my 0, -1, -1.24 is over here, -0.58 is right there. So that's a good chunk. I'd say maybe 30% again. I was wrong the last time I said 30%. Let's see how I am here. We're going to go from -1.24 to -0.58. 17%, way off. 0.1734. All right, so 17% of the data is right there. All right, 14-year-old boys have a cholesterol level with a mean of 170 milligrams per deciliter and a standard deviation of 30 milligrams per deciliter. Follow the steps to find the percent of 14-year-old boys who have a cholesterol level over 240 milligrams per deciliter. So what we want to do is find the probability that it's going to be over 240. Now before we were dealing with z-scores, so we need to turn this into a z-score. So this is the same probability that my z-score is going to be 240 minus 170 all over 30. Remember, you take your x value minus your mean divided by the standard deviation. So that is going to be 70 over 30, which is 7/3. So if I drew this out, there's two ways you can draw it out. You can draw it out using the x values or the z values. Let's try this one with the x values. If this is 170, one standard deviation would be at 200, two standard deviations would be at 230, so 240 will be out here. So we know this is going to be a pretty small number. So let's do normal CDF from 7/3 being my minimum to my maximum being infinity. So just pick a big number, and it's 0.0098. So less than 1% of the time, you'll find people with a cholesterol level over 240. Now, what's the difference if it was less than 240 or less than or equal to 240? Now, this is a tough question, but the answer is there's no difference. The probability that x equals 240 is 0, because it's just a straight line and there's no area contained if x equals 240. It's kind of hard to wrap your head around, but the probability of one thing actually happening is 0. What is the percent of 14-year-old boys who have a cholesterol level between 200 and 220? So what we do is the probability that my x value is between 200 and 220 is the probability that my z-score is 200 minus 170 over 30. Now I switch to z, 220 minus 170 over 30. So that's the probability. This would be 30 over 30, which would be 1. And this would be 5/3. So what's the probability? It's between 1 and 5/3. And if we draw it out like this, 170, 200, 230. So between 200 and 220, I'd say that's about 10%. We'll check it out on the calculator. Normal CDF between 1 and 5/3. So that's 11%. So 0.11. All right. Now what is the z-score if the numbers are smaller or larger than in your table? So if you're using the table, if it's smaller, it would be essentially 0. And if it's greater, it'll be essentially 1. All right, now here's a new problem. Consider babies born are normal in the normal range between 37 and 43 weeks of gestation. Extensive data supports the assumption that for such babies born in the U.S., birth weight is normally distributed with a mean of 3,432 grams and a standard deviation of 482 grams. What is the probability that the birth weight of a randomly chosen baby is less than 4,000? So we're going to look for the probability that my value is less than 4,000. So that would be the probability that my z-score will be less than 4,000 minus 4,003 or 3,432 divided by 482. So that's the probability that my z is less than, I'll take out my trusty calculator for this one, 4,000 minus 3432, 568, divide that by 482, and it's 1.178. So the probability that my z is less than that, I'm going to do a normal CDF from negative 1,000, or big number, all the way up to 1.178, and that's 0.88, so about 88%. Now, if I drew my normal distribution, my mean would be 3432. Standard deviation would be 482, and we would do 4,000 and less, so it'd be like this. And that looks like it could be. That makes sense that my answer is about 88%. What is the probability that a baby in this type would be more than 3,000? So probability that x is greater than 3,000 is the probability that my z-score is greater than 3,000 minus 3432 divided by my standard deviation, which is 482. So that's the probability that my z is greater than, pull up the calculator. Now we have 3,000 minus 3432. I don't need a parentheses there. And then divide that answer by 482. So that's negative 0.895, did I see? 8962. So if we want to find that it's more than 3,000, we want to do that as my minimum in my normal CDF. Negative 0.8962 to infinity. So just make a whole bunch of zeros and hit your enter. So that's 81.49%, or 0.8149. So what's the probability it's between 3,000 and 4,000? So the probability that my x value is between 3,000 and 4,000 is the probability that my z-score is between those two z-scores that we have. We don't need to find it again because we have it. Negative 0.8962, negative 0.8962, and 4,000 was 1.178. So I can just go to my calculator, do a normal CDF of negative 0.8962 until 1.178. That's 0.6955. All right, now that one's relatively the same. This one's a little bit different. What is the 30th percentile for baby weights? Now to do this one, we have to go in the opposite direction. So what we'll have to do is inverse norm. So we do second vars. Inverse norm is number 3. 0.3 is this would give us the z-score. So if I did that, we just get the z-score. But if I typed in the mean and standard deviation, let's go back so we can see that, then it will give me the actual value. So if I type in 3432, comma 482, enter, 3179. So 3,179.23.24 grams will be the 30th percentile for baby weights. All right, now here's your homework. Good luck.